Hello class, welcome to this video on the 11.1 practice. So we're going to look at we're on the homework, there's 2 questions that you need to do, but we're going to go over all 3 questions. All right, so let's look at the first one. It says every road has one at some point. Construction zones that have much lower speed limits. To see if drivers obey these lower speed limits, a police officer uses a radar gun to measure the speed in miles per hour of a random sample of 10 drivers in a 25 mile per hour construction zone. Here are the data. So is there convincing evidence at the alpha equals 0.01 significance level that the average speed of drivers in this construction zone is greater than the posted speed limit? That's a good question. So let's see if we can perform a significance test for that. So first off, what kind of significance test are we going to do? We're going to need to state our and make our plan, right? So here we are. So what are our hypotheses first off? So let's do that. So we're going to do HO and then HA, right? So our null hypothesis is that the average speed, right? The average speed is equal to the speed limit, right? Which is 25 mile per hour speed limit or construction zone. So we're going to say that it is equal to, and then we want to see, is it greater than the posted speed limit for their average? We suspect that it's greater than, so is that true? So those are our hypotheses, and then we're going to have to identify mu. So what is mu? Where mu equals the average, or I guess we should say the true mean speed, so we can be more technical here, the true value, right? The true mean speed of all drivers in construction zone. All right, and then plan. So what kind of test are we doing? So here we're doing a 1 sample t-test for mu. And then we'll look at our conditions. So we got a random condition. So here we got, it says a random sample of 10 drivers. So check on that, 10%. We can assume that the 10 drivers are less than 10% of all drivers in the construction zone. Or yeah, so just less than 10% of all drivers. And then the normal large sample condition. You can say 10 is less than 30. And so we're going to have to make a graph, okay? So I'm going to say sample is small, but now we're going to do the dot plot, okay? So let's construct a dot plot for this. And they give us the data. It's only 10, so it's not too bad. So I'm going to do the speed in miles per hour. And okay, so let's look at it. So the smallest speed is around the mid 20s, actually low 20s. 21 is the lowest, and 34 is the highest. Okay, so we're going to go from 20 to 34 or 36, something like that, and we'll go by 2. All right, so we got, so looking at our data, so we're going to go ahead and quickly graph that. We got 21, 2 27s, got a 29, got 2 30s, 32, 33, and 34. Okay, so there it is. So then looking at our data, we can say that, okay, well, the dot plot or our graph, the dot plot doesn't show strong skewness or outliers. Okay, so it looks pretty good. And then let's do the do. So now we're going to need to plug this in and get our statistics, right? So our X bar, we're going to need to get our standard deviation, and then we're going to also need to get our t-score, right? Our critical value, and all that good stuff. Okay, so let's do our df. Our df is 10 minus 1, which is 9. And then we're going to need to find we're going to need to calculate our not our t star. I'm sorry. We're going to need to calculate our t. But first, to calculate t, we need to know x bar and sx. So we're going to plug this into the calculator, see what we get. Okay, we're going to go ahead and hit stat and then edit, and then we typed in the data. I typed in all the speeds. Okay, so there's 10 of them in total. And then I'm going to go stat, calculate, 1var stats, list 1. We're going to calculate that. So we get our average speed, which is 28.8 miles per hour. We get our standard deviation, 3.9. We'll round it to 3.94. All right, so we got 28.8 miles per hour. We got 3.94 miles per hour. All right, and then we're going to calculate our t. So t is equal to x bar minus mu divided by mu 0, where the mu 0 is for the null hypothesis value, and then over sx over square root of n. Okay, and then we know that, so let's calculate that. So x bar is 28.8 minus, now the null value is 25, right? That's the hypothesis. It was 25 over, okay, over 3.94 divided by square root of 10. Okay, if you calculate that, you get about 3.05 for your t-score. All right, so now we got our t-score. Now we're going to draw the graph real quick. So we got, this is my t distribution. And we got t is 3.05. So this is my t value. Now remember, if I go to my test, it's a right-tailed test because it's pointing in the right direction, is greater than. Okay, so we're going to shade to the right of that, and that we got to find the p-value. Okay, all right, so the p-value, we can calculate that using tcdf. All right, so we're going to use the tcdf function. We got our lower value, our lower limit. Our lower limit is 3.05 based on the shaded area. Our upper limit is infinity, so just 1,000, I guess you can put. And then our degrees of freedom is 9. Okay, and we can calculate the p-value using that function. We can also look this up because we know 3.0. Oh yeah, so there's two ways to do this. You can use the table or you can use the calculator, the tcdf for this. I'm going to suggest using the calculator. That is the best way to do this because you want to, just to get a more accurate calculation. So I'm going to use that. Although, even though I will use that, I will show you how to use the table as well. So if you have 9 degrees of freedom, t is 3.05. Let's go to the table. You got 9 degrees of freedom, and we got we need the so we got 9 degrees of freedom. We got t is 3.05. So which is closest to that? So 3.05 is between these two values, which means that the p-value must be between 0.005 and 0.01. Okay, so 0.005 and 0.01. So let's go back. So we know that the p-value is between 0.005 and 0.01. And we're going to calculate this. We're going to do this on the calculator. Okay, so let's do it on the calculator. So we're going to go to second vars. We're going to go to TCDF and change that. That's 3.05. That's 1,000. And the degrees of freedom here, how many was that? That was 9. Okay, and enter. And so this is my p-value. All right, so 0.0069, we can round it. All right, so our p-value is approximately 0.0069, which, lo and behold, is between 0.005 and 0.01. That's what we were saying. Okay, in any case, you can see that this is less than alpha, right? Our alpha, we actually need to specify. It's oh, I forgot to specify the alpha here. So construction zone for alpha equals 0.01. So that was our alpha. So it's either way, it's going to be less than 0.01 because it literally says right there is less than 0.01, right? Between 0.005 and 0.01. All right, so we can go ahead and conclude. But before we do that, I want to show you how to, one more thing on the calculator, show you how to do this whole test on the calculator. Okay, so let's show you how to do this whole test on the calculator. So we're going to go to Stat, we're going to go to Tests, then we are going to do we're doing a t-test, right? So we're going to do a t-test. And here we have statistics, so we can just plug them in. So what was our mu0? So that's 25 miles per hour. Our x-bar was 28.8. This one was 3.94 is what we rounded it to. And then we got 10 for the, actually we did have data. I forgot that we had data. So actually let's go to data because we actually have the data. So let me do that. Sorry about that. Our mu0 is 25. We have our data from list 1. Now, which direction? Not equal to, less than, or greater than? It was greater than, right? And then we're going to calculate. And here we go. So we got that. Oops, let me go back to that. Let me go back to that test because I messed that up. All right, so we got t is 3.05. We got our p-value, which is 0.00688, and so notice you get the same values. Okay, now that we showed you that, let's go ahead and conclude. So we're gonna conclude that we're gonna need to reject HO because the p-value is less than alpha. Okay, because p-value of 0.0069 is less than alpha, which is 0.01. We reject H sub 0, or HO. We have convincing evidence that the true mean speed of all drivers in the construction zone is greater than 25 miles per hour. So we actually find that it is significant, you know. So interestingly enough, the average was 28.8, and that is significant. All right, so now we can look at the next question. So given your conclusion in part A, what kind of mistake, a type 1 or type 2 error, could you have made? Explain what this mistake would mean in context. Okay, so, well, because we rejected HO, we could have made a type 1 error, right? Because, you know, it could have been an error. Maybe we didn't have to reject HO because maybe it was true, right? So, so we could have, given our conclusion, we could have made a type 1 error. Explain what this mistake would mean in context. So we want to explain this, okay? What this would mean in context is that we would be finding convincing evidence that the true mean speed is greater than 25 miles per hour, which is what we were saying, when it really isn't. Okay, so maybe we made a mistake. We send too many cops out there to use radar guns. We waste resources because maybe the speed actually isn't greater than, maybe it actually really isn't, the average of the driver's speeds isn't greater than the true mean speed, and so we really don't have to send cops and other resources in that area. So we could be wasting money, right? Rather than being in a zone where it actually is a greater average speed. So these are consequences, natural consequences. All right, so number 2, student researchers Haley, Jeff, and Nathan saw an article on the internet claiming that the average vertical jump for teens was 15 inches. They wondered if the average vertical jump at their school differed from 15, so they obtained a list of student names, selected a random sample of 20 students. After contacting these students several times, they finally convinced them to allow the vertical jumps to be measured. Here are the data. Do these data provide convincing evidence at the 0.10 level that the average vertical jump at the school differs from 15 inches? Okay, so let's look at it. So here we're gonna do a test. So let's go ahead and do the stage. So let's do our HO and our HA. So our HO, we're dealing with means. So we got mu. Okay, so it says that it differs from 15 inches. So that means it could be equal to or it could be different from 15. All right, and then let's identify what does mu stand for. So mu is the true mean vertical jump of all students at this school. Okay, so there you go. So now let's plan. All right, so what kind of test? We got a one sample t-test for mu. Let's do the conditions. So random condition. They did say that they had a random sample. If you go here, it says they tend to list of student names and selected a random sample of 20 students. So it looks like they did a simple random sample here. So they did a random sample of 20 students. So 10% condition, we're going to assume that 20 is less than 10% of all students at the school. And normal large sample. Sample size is small because n is less than 30. But now this is where we need to make a dot plot or a graph or something like that, okay? So this is the part that takes the longest, is making that dot plot. All right, so let's go small. All right, so let's just go by, let's start at 5. And then we're going to technically go by, fives here. There. And then the highest is in the 20s. Yeah, 26.5. So we'll go up to 30. And then technically we're going to go by 0.5s here. So that's going to be 1. That's 2, 3. Hold on, I need to make sure I do this right. One, 2, 4, and then 4.5. All right, and then we got 1, 2, 3, 4, 4.5, and then 5. Okay. All right, so there you go. And then, so each of these is 0.5, and then we can just graph them. So if I go over to our data, this isn't too bad because there's a few copies. So all we got to do is just graph the numbers. They're all 0.5s or 0, so this makes it easier. All right, so I went ahead and just graphed it just to save some time. So you get something that looks like that. And we got, this is going to be our vertical jump, which is in inches. Okay, all right, so now we can say the sample size is small, but if I look at that, there is no strong skewness or outliers in the sample. Okay, so it's reasonable to use the T procedure, and in fact, this is taking up a lot of room, so I'm gonna bring it up a little bit. There you go. All right, and then we'll go ahead and do the do stage. So now we're gonna go ahead and do. Okay, so now let's go ahead and calculate our statistics here. So we got X bar, we got SX. Again, they give us our data so we can calculate that. So again, if you did that on the calculator, you would get 17 for the average vertical jump distance. You would get 5.368 for the standard deviation. Again, I've showed you how to do that on the calculator, so it's just a matter of doing it. Now, degree of freedom, there's 20 students minus 1, so it's 19. We can calculate the T. Again, it's X bar minus mu 0 over SX divided by square root of n. We get 17 minus the mu value, which is, I don't remember, 15. All right, so you got 1.67 for the T score. Then we can calculate the p-value. Well, I'm going to make a little graph here for T. And our T is 1.67. And it is a two-tailed test, does not equal 2. So we actually have a negative version as well. So we're shading both sides here. So when we do the p-value, we need to figure out what it is on one side and then double it, okay? So when I do the p-value here, let's say p-value, we can use the TCDF function, but then we got to double it, okay? So I'm going to do 2 times the TCDF function, and we're going to do this area on the left. So that means it's going to be negative infinity. The lower is negative 1,000. The upper is negative 1.67. And then our degree of freedom is 19. And we will need to calculate that. But if you calculate that, I've showed you how to do that already, then you double it. You're going to get a p-value of, let's see what we get, around 0.1121. All right, which now if I compare that to my alpha, our alpha, and I forgot to put that, this is for alpha equals 0.10. So we compare that to 0.10, this is greater than that, which means we're going to fail to reject. Okay, so this is important. If you had done this as a one-tailed test, then you would have gotten like 0.05 something, and that would have been less than 0.10, and you would have rejected. But remember, it's a two-tailed test, so it's actually failed to reject. So that's important. All right, so conclude. So we're going to conclude that we need to fail to reject, right? Because it's greater than. So because p-value of 0.1121 is greater than alpha equals 0.10, we fail to reject HO. that means we don't. So we don't have convincing evidence that the true mean, I was gonna say jump distance, but it's vertical, jump distance for all students at the school is different from 15 inches. All right, so let's look at the next part. The next part is a 90% confidence interval for the true mean vertical jump distance is 14.924 and 19.076. Explain how this interval gives more information than the test in part A. Okay, well that's kind of it gives you more information because obviously you get the limits, right? So you actually know, like, okay, 90% of the value, we know we have the limits of the data. So it tells us that any value of mu between these two values is considered plausible, right? Based on the sample. Okay, so I'm going to say part A. So part A only allowed us to fail to reject HO. But the confidence interval, I'm just going to say CI, okay? But the confidence interval tells us the range of plausible values for mu are between 14.924 and 19.076 based on the sample. Okay, so this gives us more information about the plausible values. So now it says the power of the test to detect that mu equals 17 inches is 0.49. So they want you to interpret that value. So remember that the power of a test is the probability that you would find convincing evidence for the alternative hypothesis given a specific value is true. So given that we know a specific value is true, in this case that mu equals 17, given that we know that's the actual value, then the probability that if we did the test that we would find convincing evidence is 0.449. So that's what we're talking about here, okay? So we're going to say if the true mean jump distance of the students at the school is mu equals 17 inches, then there is a 0.49 probability that the student researchers would find convincing evidence for HA. Okay, so that's what power means. Now find the probability of a type 2 error if mu equals 17. This is easy because we know that the power is equal to 1 minus the probability of a type 2 error. And so if I solve for type 2 error, then that's simply going to be, I'm sorry, if I solve for the probability of type 2 error, that's going to be simply 1 minus the power. So it's 1 minus 0.49, which is 0.51. So the probability of making a type 2 error is 0.51. Right? So describe 2 ways to decrease the probability in part D. So if I want to decrease type 2 error, right, what I need to do is I need to, first off, based on this equation, if I want to decrease type 2 error, that means, that means I need to increase the power, right? If I increase the power, that's going to decrease the type 2 error. So how do I increase the power? Well, to increase the power, you can increase the sample size, okay? So increasing the sample size increases the power, okay? So the more sample size, the more representation you have, then you have a stronger test, okay? You increase the sample size, or what you could do is, if you want to decrease type 2, then you could increase type 1. Or rather, yeah. So technically, if you increase type 1, then you decrease type 2, and vice versa, right? But yeah, so we can use a larger significance level. So we could increase alpha, the significance level. Okay, so alpha is a significance level, because remember, alpha is also the type 1 error. So if I increase alpha, I decrease type 2. Okay, so that's a couple ways to do it. All right, so I was going to do example 3, but I decided to cut the video short because it's pretty long at this point. So hopefully you find this useful and informative, and as usual, I'll see you in the next one.